Those Milankovitch cycles, or these orbital parameters, explain a lot of the variability in climate, but they have another interesting feature. Because it's celestial mechanics, you can effectively calculate a solution for all three of the parameters back in time. You can predict what eccentricity should have been, let's say, 1 million, 2 million, 5 million years in the past. You can predict what obliquity should have been. You can predict what the precession should have been. And having these three parameters, you can then calculate an insolation value for the surface of the Earth at any one point in time. So that's an incredible predictive tool to see what paleoclimate should have been, but also it offers a great way of dating sediments, because if you know what the insolation parameter should be, you can then, by definition, know at what time it should have been like this and tie this to a record that you have in your sediments. And here's an example of a solution calculated using celestial mechanics by Jacques Lascar in 2004. And this diagram looks a little bit complicated at first, so let's see what's going on here. You have to realize that we're looking at a time series that has been sliced into 5 different mini time series. So the time starts on the right and goes to the left. So this is eccentricity from 0 to 5 million years in the past, from 5 million to 10 million years in the past, from 10 million to 15 million years in the past, 15 to 20, and finally 20 to 25 million years in the past. So here you have the solution for eccentricity calculated for the last 25 million years by Jacques Lascar. Notice that there are 2 curves that show up here. One is a curve that is in solid line. That's the most recent calculation of the solution. The other one is a dashed curve. That's an older solution. And the point here that Jacques Lascar is making is that when you go back in time, you accumulate potential error of your solution. So the further back in time you calculate these eccentricity and any other orbital parameter, the greater your error will be, and so the greater your uncertainty. So for practical purposes, we can calculate a solution back to the Miocene, the Eocene, potentially the Cretaceous, but if we go all the way to the Jurassic, then the system becomes quite chaotic because the error is too large. But for the more recent time slices, so let's say the last 60 million years or 30 million years, we have a fantastic record or calculated record in which we can anchor our sediments and essentially do chronostratigraphy, which is known in this case as cyclostratigraphy, using cycles to date sediments. So what are the principles of cyclostratigraphy? Well, you need a few things to be able to do cyclostratigraphy. First, you need a complete record without gap. This means that deep water sediments are much better suited for cyclostratigraphy than shallow water sequences where sequence stratigraphy is easy to apply. So that's one thing to keep in mind. The second thing is you need to have dating. Just using cycles to correlate cycles with a solution known as an ETP is not good enough. You need to be able to have independent dating. So some form of biostratigraphy or chemostratigraphy or absolute dating is needed. Then of course you need to have a record of cycles. You need to be able to see your cycles. So that could be anything. That could be carbonate content, that could be lithology, that could be delta O18. It doesn't really matter what it is, but you need to have a record with cycles in it. And you need to be able to find a ratio of cycles that is a ratio that you would naturally find in Milankovitch cycles. And finally, of course, you need to have an understanding of how your record ties to the forcing mechanism, ties to the orbital parameter themselves. So let's look at this in detail and step by step. So the first step is to identify cycles. And I show you this beautiful example here, which actually comes from relatively shallow water deposit, basinal deposits in the Mississippian carbonates So that's a North American record. And the point here is that you see bedding and that these beds have been interpreted by the author as representing precession cycles. Now you know that a precession cycle is about 20,000 years. So assuming that the authors are correct and that this is a complete record of precession, what's amazing is you're looking at Carboniferous sediments, but Carboniferous sediments that you can date with a precision of plus minus 20,000 years. And this is a great thing about orbital tuning, is that the precision that you get is as good as your cycles, but of course the risk is to miss some cycles and so make a mistake that you can't really control. That's why independent dating is still absolutely vital. The second step is to look at the cycle ratios in meters and see if they correspond to any Milankovitch ratio. So for instance, here we're looking at a magnetic susceptibility record in a section, and that's in meters from 0 to 12 meters. And if you look at the frequency of the occurrence of those laminated shales versus the mudstone or shales, you can see that we have one first peak of occurrence at 1.23 meters, so that could be your first rhythm or your first cycle. And the second is at 0.62 meters. So now doing very simple math, you can see that this corresponds almost to a ratio of 1 to 2. And what Milankovitch cycles occur in a ratio of 1 to 2? Well, for instance, obliquity, 40,000 years, and precession, about 20,000 years, that's a ratio of 1 to 2. And indeed, if you look at this section, the interpretation is that you're looking at some precession cycle and also a control from the obliquity cycle. And this is why looking at the ratio of cycles in meters is so important, because it already gives you an indication of whether or not it's reasonable to assume that what you see is forced by orbital parameters. And if it is, then you can go to the next step, which is to do the tuning itself.